Okay, so yeah, it seems that all the classes did really well yesterday. Things got kind of hectic though because I have IB students in some of my pre-cal classes, and all of my other pre-cal classes, the substitute was trying to pass this information out to him. Did he try to pass out the material from the pre-cal classes to you, or that did not become a problem? Okay. All right, so we're good. We're good. I really want to know where he got his hands on the copy of the homework. That's interesting because I didn't send that in the email. Anyways, this is what we're going to go ahead and start talking about today. Right triangle trigonometry. Okay, these are the notes that should have gone out yesterday, just so you guys can go ahead and start looking at them. So a lot of this is going to be, hopefully all of it's just going to be a review. I'm going to help you maybe fill in some gaps if you'd had those the first time around when you saw this in geometry. But just a couple of key items up here at the top. The sum of the interior angles of any triangle is always 180 degrees. Okay, the sum of the lengths of any two sides must be greater than the length of the third side. The smallest side is across from the smallest angle, and the largest side across from the largest angle. Okay, we remember that. In a right triangle, the hypotenuse is directly across from the right angle and is the longest side. Okay, the two legs that form the right angle, okay, two sides I should say, we call those legs. Right triangle, one interior angle of the triangle is 90 degrees. Equilateral, all interior angles of the triangle are 60 degrees and all sides are of equal length. Isosceles triangle, two sides of a triangle are of equal length. So what do we call it if all of the angles are the same in any figure? Now, equilateral is all side lengths are the same. Equiangular. Now, do you guys remember it's not on here, and it's not going to be one that you're tested in IB, but just to kind of see if you remember it, what do we call a figure that is both equilateral and equiangular? Starts with an R. We call those regular figures. That is very good. Very good. Okay. In fact, does anybody remember what do we call a triangle that does not have a 90-degree angle? Starts with an O. Oh, it's not obtuse. Not obsolete. Oblique. It's actually very, very similar to that. Oblique. Okay. Or you probably have heard the term scalene, where if all three of the sides are not of the same length. Okay. All right. So our special right triangles, we're going to be seeing these a lot, a 45, 45, 90 and a 30, 60, 90. So instead of the A, B, and C, I want to go ahead and talk to you about the relationship that the three have, because you're already familiar with the Pythagorean theorem, right? Which says what? Yeah, A squared plus B squared. The sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. Okay, but these triangles are special. You need at least two sides in order to use the Pythagorean theorem, but with a special right triangle, you only need one side in order to find the remaining two. Now, this right triangle here, the 45, 45, 90, it's the only isosceles right triangle that we have. So the side lengths, we always put them in terms of x units, whatever our measurement is. Okay, so what do I do to the side x, the leg, in order to get the hypotenuse? X times what? What's the relationship? We multiply it by some radical.
Oh, root 2.
Root 2, there we go. So x square root of 2. Now, when we're dealing with a 30, 60, 90, okay, the shorter leg is always going to be across from 30, and he is going to be x. He's going to be the shorter leg. So what do I do with the shorter leg to get the longer leg? I multiply him by something.
Root 3.
Okay, square root of 3. So this length would be x square root of 3. And how do I get the hypotenuse using the shorter leg? 2x. It's always double the smallest leg. There you go. So if you take a look, no matter what side you have, you can always work backwards because they all have x in common. You might need to set up a small little equation, rationalize if necessary. Okay. But now, trig ratios. There are actually 6 total. We're only going to be looking at sine, cosine, and tangent. The other 3 are their reciprocals. Like, what's the reciprocal of sine? Oh, no, that is actually something different. Cosecant. There we go. What's the reciprocal of cosine? Secant. And what's the reciprocal of tangent? Cotangent. Okay, so good, good, good. So some people already remember all this. Hopefully it's the students I taught in pre-cal. Okay, and calculus too. You have those. Okay, very good. But we're only going to be responsible for these three. So here's the thing: how a trig function works. If you go ahead, okay, let me get this right here. Like, let me take sine for example. Whatever you plug into a trig function, it's an angle measure. Now, whether that's degrees or radians, and in here we're going to be looking exclusively at degrees. Okay, so if you want me to bring up radians, I can, but it's not necessary unless you just really want to know about it. But every time I evaluate a trig function using an angle measure, again in degrees, I'm going to get a ratio of the sides of a triangle. And each trig function is very specific about what sides they want. So sine is always going to take the opposite side over the hypotenuse. Cosine is the adjacent over hypotenuse. Tangent is the opposite over adjacent. In fact, that is where you get SOHCAHTOA from. SOH, sine, opposite, hypotenuse. Okay? CAH, cosine, adjacent, hypotenuse. And then TOA, tangent, opposite over adjacent. Okay? The only thing you have to be really careful of is what angle you're referring to. Because here, if I was talking about this angle, and let's say it's X degrees, then the side directly across from it is the opposite. The one that's next to it, that's the adjacent. And of course, what's across from 90, that's got to be your hypotenuse, right? But if I were to talk about this angle right here, okay, well, this is X degrees. Let's call this theta. Then from theta's perspective, this would be the opposite side, while this would be the adjacent. Okay? So it does depend on what angle you're referring to. Is everybody okay with that? As you switch angles, those sides are going to switch, not the hypotenuse. The hypotenuse is always going to be across from 90 degrees. Okay. Yes.
What do we do if we're given like the two side lengths and we're called to ask the degrees of theta? How do we do that?
That you have to take the inverse. Now, I'll probably get more into that tomorrow, but the idea here, you remember how I said you evaluate any trig function at an angle and you get a side ratio? Well, they're very specific. Okay. So there you go. With the inverse, remember, you take the input and the output, the x's and the y's, and you do what? You flip them. So if I were given the ratio, if I had the side lengths but I wanted the angle, then I'd take the sine inverse of the ratio, and that would give me the angle measure.
And the ratio stays the same. You don't like flip the ratio or anything?
No. The ratio will stay the same. Now, the ratio only changes if you take, like, the reciprocal. So, like, if I were to, give you something like, sine of 30 degrees is equal to 1/2. Well, remember we said a second ago, what's the reciprocal? What was the reciprocal trig function? And you're not going to be responsible for this, but just for fun. Cosecant. So I could say cosecant of 30 degrees is equal to 2. It's the reciprocal, so I just took the reciprocal. So see, while sine is always opposite over hypotenuse, cosecant would be the hypotenuse over the opposite, 2/1. Okay. All right, good. And again, something you're probably not going to be responsible for, but I thought probably not a bad idea since we're bringing up trig to go ahead and show you the graphs. Here's sine, here's cosine right here. Both have a period of 2 pi. That means that's how much measurement is needed before the graph repeats itself. Basically, you're talking about revolving around the unit circle in either direction. Okay. Oh, now I almost didn't want to show you this. My tan line is showing. Tan line. Good. That's a good one, right?
And in West Texas, you call it a farmer's tan, and farmers did trig.
What?
You know what a farmer's tan is?
I have not.
It's like where you like t-shirt gives you like a t-shirt tan.
Uh-huh.
Where, like,
Okay, and what? And we call that a farmer's tan here?
Yeah, I call it a farmer's tan.
I guess I've not heard of that.
Look at that.
See, we learn something new every day. All right. So the next time I'm walking along and I see a guy with like a pretty distinct tan line right there, farmer. Then I'll say something like, "I can dig it." Because farmers dig, they plant. Well, back in the olden days, I'm sure some still have shovels. Okay. All right. So angle measurements. Degrees, minutes, seconds. And if I want to go to just specific degrees, this I'm not going to go ahead and spend a whole lot of time on. You can go ahead and do it by hand, and as is shown here. I think when it comes to degrees, minutes, seconds, or just specific degrees, it's probably easier to just go ahead and show you this in the calculator. Okay, so let's say I have this right here. Okay, so the 1 tick mark means what? Minutes. The 2 tick marks means should be seconds. Oh, I'm sorry, I was looking at the wrong one. Seconds. So it's degrees, minutes, seconds. So if I wanted to know specifically just what degree measure that was, well, this is what I would do. I'm going to go to my calculator. And there's different ways to do this, but if you were to go right over here, let me get rid of this, document B. In fact, we were taking the inverse cosine function for vectors and pre-calculus. But if you go right over here, this button right between 9 and the catalog, okay, right here, if I go ahead and click it, okay, you'll notice the second one right here, second row, second item. When I click it, see, it gives me just the blanks, and I can put in whatever my degrees, minutes, and seconds are. The 1 tick mark is minutes. The 2 tick marks are going to be seconds. So in this case, what do we have here? It's 42, 12, 36. So I'm going to type in 42, 12, 36. So 42 degrees, 12 minutes, 36 seconds. If I click enter, okay, and then control enter because it's going to give me the decimal, there's the 42.21 that we originally had. Okay. Now, if I have a degree measure and I want to go to degrees, minutes, seconds, well, what I'm going to do, let's just take this one right here, the 42.21. So once you type it in, this button right here, that's the open book, the catalog, okay, you're going to click it, and you're going to want the first tab open. So if the first tab isn't open, you can use the touch pad on your calculator, use your mouse, go ahead and, highlight it, push it. So you're going to want DMS. Okay, what do you think that stands for? Degree, minutes, seconds. So you'll type in your degree measure, put in DMS, the command, and it gets you right back to degrees, minutes, seconds. Okay. Like, I always think there's value in doing these by hand, but this is probably one of those rare occasions where I would just say, don't worry about doing it by hand. You got the calculator, just go with it. Okay. All right. So any questions on how I did either?
What exactly are degrees, minutes, seconds?
It's a way of getting a more specific location. Have you ever heard, like in movies and TV, where on a naval ship, they'll say 42 degrees, 5 minutes, 7 seconds? It's just ways of measuring degrees in a different notation. Yeah. Okay. Like, honestly, it's part of the lesson here, but I've never seen it show up on a paper exam. So it's just one of the items that is brought up. Okay. But if it is brought up, the calculator is going to be the way to go on this one. Okay. Normally in pre-cal, I teach that by hand, but I'm not worried about it. Okay. All right. Now, angle of elevation and angle of depression. These are some pretty important phrases that we'll need to know. Angle of elevation, the angle of sight above the horizontal. So it could be, from the ground rotated up, or it could be from a person's line of sight. They were looking directly ahead, and that was horizontal to the ground. So the elevation is where you look up from that position. The angle of depression is if you were to look down. Okay, so if I'm standing on the ground and I see a plane in the sky, I could look up at an angle of elevation of so many degrees until I reach the plane, right? Or maybe conversely, I'm standing on a cliff, maybe by the ocean, and I see a ship out in the ocean, and I just look down, so that's the angle of depression. That makes sense, right? Okay. All right. So let's get right to an example. Given right triangle, ABC, where C is equal to 90 degrees, we can tell by that little box there, solve the triangle. Now, typically, whenever you're told to solve a triangle, that's really asking you to find every missing angle and every missing side length that there is. Okay. So we also know that A is equal to 5, and here's how we do this in geometry. The capital letters represent your angle measures. Okay. So that means the lowercase are your Your side lengths. So side A will always be opposite angle A. So I know this one here has got to be 5. Okay. So I also know that angle A is 52 degrees. Okay. All right. And it looks like I have everything I need. So where do you suggest I go now?
We can do line BA.
Line BA. So segment BA, that would be the what?
Uh,
Starts with a H.
hypotenuse.
The hypotenuse. Okay. How would you suggest I get that?
So you can use sine of 52
Okay.
is 5 over x.
There you go. So see, I'm saying I'm using this angle right here, so that means 5 is the opposite side, and this hypotenuse, you can say hypotenuse, you can label it as x, basically whatever variable you want. But you go ahead and create the ratio of the sides, the fraction of the sides, using the specific trig function. So the opposite is 5 over hypotenuse, I'll just say it's x. And then, yeah, you're just solving your equation. Okay. So how would you like me to solve this equation?
So you multiply both sides by x.
Okay, so let's multiply both sides by x. So those are going to cancel. So x times the sine of 52 is equal to 5. There you go. And now divide through by sine of 52. Because anything divided by itself will cancel, even a trig function. Okay. Now, the only thing is, we're not going to be dealing with radians in here. How many people are familiar with what radians are? Okay, if you are, that's great. If not, don't worry about it. Okay, but there's always a test I do. You always want to make sure that your calculator is in degree mode. And because these calculators are also being used in pre-calculus, where we do deal with radians, it's a safe bet that occasionally the mode is going to be changed, even though I always tell the students keep it in degree. A quick test is just, here's your trig function right here, right next to the 7. Okay, here's what I always do, even though mine says degrees. If I take sine of 30, if it gives me 0.5 or 1/2, I know I'm in degrees. Okay, that's always a quick little test. Sine of 30 has got to give you 1/2. So here, we want to know, well, 5 divided by, what was it, sine of 52? Okay, so as soon as I push enter, I'd say the hypotenuse is probably like 6.35. Okay. So we'll take it to 3 sig figs, 6.35. Okay, so let me take that off right there. Okay. Now there's also something else that we can find without a whole lot of work. We can, but what's even easier? We need to find angle B. Okay. Well, think about it. If all 3 angles are always going to add to 180 and you're in a right triangle, well, 90 plus what's going to give you 180? Okay, 90. So I know that 52 plus whatever angle B is would have to equal 90 as well. So you don't always have to subtract from 180. So basically, what's 90 minus 52? 38. There you go. Okay. And you could use a couple of different equations to go ahead and help us out. We could say cosine of 52 equals the adjacent, okay, over the 6.35. Or we could go ahead and use 38. We could say sine the opposite over the hypotenuse. Because again, remember, it depends on which angle you're going to use. That's going to determine the sides. Okay, so Graceland, what do you like? Do you like the 52 or the 38? The 52. So if we're going to stick with the 52, okay, then this side becomes the adjacent. The opposite stays the same, and we know the hypotenuse. Okay. All right. So what should I use? Sine, cosine, or tangent? Cosine. Okay. So I would say cosine of 52. Now remember, it's always the adjacent side over the hypotenuse. So the adjacent, well, let's just go ahead and use y this time because we already used x. We just want to use a different variable. Okay. Over 6.35. Would everybody agree? Okay. Now here's what I like to do. especially if I'm not given exact numbers. Like this is a decimal place that's going to continue forever, right? When I write it on my paper, I'm going to go ahead and round it to a certain number of places. But when I solve, I'm going to go ahead and use the actual value in the calculator to get a more approximate answer. Does that make sense? So I'm not going to type in 6.35. I'm going to go ahead and do this. I'm going to go ahead and use the previous times cosine of 52 degrees. Now, we're not talking about anything that's going to be off by a huge amount, but it's just a habit I've gotten into teaching pre-cal these past few years. Okay. So when I push enter, I would say that other length is about 3.91. Okay. Whatever unit of measurement we have here. Centimeters or inches or whatever. Okay. So adjacent 3.91. There we go. Okay. Questions? Okay, so tomorrow we'll do another one of these examples. We'll talk a little about inverses, okay, and then we will finish everything up. Okay.